Hello. In this video, I'll speak of the error surfaces and an error report produced by the L-Range modeling family. The logic behind the need for these surfaces follows from what was addressed in other videos as the biogeochemical representation included in the L-Range family as coming from primarily the Century model. As I've talked about, the Century model is point-based, meaning that the area could be a square meter that it's representing, or a pasture, or even a county, but it's an area, a single area that's judged sufficiently homogeneous that a single set of parameters can represent that area, and we speak of that as point-based. Now, in that logic, if you have a model in place, you run it, and it works, then of course you just go about your business, continue with your analyses. If it fails, you need to find out why, fix it, and then move on. That same logic wouldn't work very well in L-Range. There are thousands of pixels being represented in most L-Range applications, and so having the model just crash if there's one that's wrong would be really inconvenient. It'd be difficult to get correct. It'd be difficult to know where the errors were occurring. And so a real challenge in that regard. And so I had to come up with a separate pathway. What I did was in computer science to call trap these errors, to capture them and to record them in the most complete way I could. Now, a couple of options there. I could have produced error surfaces for every one of the outputs that are produced by L-Range. More than 100 surfaces can be produced. And I could have had 100 more surfaces that reported the error for each surface. But that seemed very unreasonable to me. It would just double the amount of space required and be quite awkward. And so I took another pathway that I'll review. Here is a graphical user interface for AFRange, an application of L-Range to Africa that will soon be available. This is a draft application. Here you see precipitation for the first year of the simulation, and below there's a graph. So if you clicked on some of these cells, you'd get a graph of precipitation, but I've cropped that out to enlarge the size of the map. And so we have, as you might expect, we've got precipitation and maximum temperature. We've got bare cover, for example. Now, it is the case that some of these pixels may cause problems for whatever reason, whether it's errors in soils data or parameters that might be a bit off, or maybe the day length is being calculated incorrectly, whatever the case. And if that happens, there can be errors that follow from that. Happens for nitrogen, for example, for various reasons. And so, again, an error shouldn't bring the whole model down. And instead, those errors were captured. Now, I didn't provide these individual surfaces I mentioned. Instead, I provided two surfaces that sum all the errors across all the output data and then give non-spatial results for the individual entries. So we could think of it as three tools, if you will, that come together to talk about error in a given simulation. I say error in a very specific way here. We're not talking about how well a model is doing at representing reality necessarily. We're talking about two things that define an error. One is if values that shouldn't go negative are going negative, like biomass shouldn't be negative, right? And so if it is going negative, here an error is captured and that value is reset to 0. The other example is if a value reaches what in computer science is called maximum integer, a very, very, very large number. If that happens because of divisions by 0 or whatever the case, if that happens, then L-Range resets that value to still a very large value, but within a reasonable range and then records the error. Those two kinds of errors are captured in reports that appear at the bottom of the list if they're enabled to be output. And so here you see a large error count, and you can see across the surface scattered yellow pixels that capture those errors, report those errors. Now, these errors are non-specific to a given data type. They could be in any result. But you can see that they appear in the Sahara and in the Kalahari, some drier areas around the landscape. This is typically a minor source of errors for L-range. More commonly, we see errors where values are going negative, but they shouldn't. Now, they could be negative by just the smallest amount, but they still get captured as an error and reported and reset to 0. Here's the surface for that in this draft application. And so you can begin to see pattern here and can consider, well, in these landscape units, there may be something off in terms of parameterization, or in this case, forest cover or the like, perhaps because of the patterning of the error. Now, for specific entries, those get reported in a text file. It's still in the output folder, but it's a text file called exceed.gof. And so you can just open this in a text editor, and it looks like this. Again, you can see there are two types of error. And so we have all the output files listed on the left. And then across the top it's speaking of the number of times each variable cell month combination exceeds a threshold and is reset for the very large error type and the negative, or in this case, it's indicated as 0 error type. And so again, if something gets very, very big, it's reset and is recorded as a very large error. If something goes below 0, it's reset to 0 and is recorded in that way. And so you can see that 3 times in this 20-year simulation, total population of plants got very large and was reset. Now, one of the ideas is that some of these numbers can get very large, and at first it's jarring. And I don't want to judge. I don't want to suggest that these errors aren't a problem for a given application. They may be, they may not be, depends upon how the tool is used. But do keep in mind that these are cell month combinations. And so when you think of the output, say, if we had a pixel, so let me bring up another file also in the output folder that's produced, and it's called rangedata.gof. You can see across the top some entries. This is meant for use. It's not really to be read, but rather used by the graphical user interface and other things. But you can see that there are the number of cells represented here, 73,960, so almost 74,000 cells being simulated in AFRange. Then just incidentally, there's the dimensions of the map, 364 by 405. There's the lower left and upper right corners in the given projection, which is an Albers projection for Africa. And then there's the resolution on the right, which shows a 20-kilometer resolution. So you see the entry for 20,000. And so it's a 20-kilometer resolution application of L-range to Africa. Then there's information for specific cells below. But really, the idea is that when you interpret these results, keep in mind that you're talking about almost 74,000 pixels being simulated. And so over the span of these 20 years of simulation, if it would be hard to imagine, but if every cell failed just once, 1 month, then this counter would go up by 74,000. Or conversely, if there were just a few cells, but they failed every month, because there are so many cells, those numbers can get large quickly. With these three resources, then, an analyst can get a sense of the relative magnitude of errors, whether it is a concern for the use of the model at hand, the spatial patterning of errors, and the types of information that are generating those errors. I'll give an example here, although it is an easier example. So we have two columns here. You can see the left-hand column with the zeros, that is for values reaching maximum integer and being reset to a very large value. And then on the right, we have values that are going below zero by whatever amount and being reset to zero. If I used an example from the zero column, it would be a little harder. Here I'll use an example from the left-hand column exceeding a very large value. And so you can recall then this map of the large error count and the scattered pixels in the driest parts of Africa. We can go back to the report, scroll down, and see that there's really one entry causing problems here, and it's Tmin up, which is actually mineralization uptake of nitrogen in decomposition. And so it's very likely associated with cells that have no vegetation at all, and the model's just not built for that. And so it's likely giving an error. And so I probably would let it go in these areas that just have no vegetation. And so in that way, one can get a sense of the, again, distribution and relative importance of these different errors and how they might be repaired if needed.